Ooh, that Snell, the Snell of it around you. Okay, so we're gonna use Snell's law again. Snell's law. But we're gonna kind of do it in a backwards way. What we're gonna do is imagine yourself, you're in a pool of water. Okay, you're in a pool of water, and outside the water is refreshing air. It's how we breathe. If you are shining a laser pointer, let's make it a green one, out from the water, so this laser pointer is gonna go out, it's gonna strike the surface of the water. If we recall, there is some normal line here. And when we do this, this will be theta 1 in this case. Now, the index of refraction of water is going to be greater than that of air. So N of H2O is greater than N, whatever air is made out of, some gas mixture. And because of this, we're actually going to speed up the ray of light whenever it leaves the water. And that means that we're going to turn away from the normal. So we're going to turn and do something like this. That's what we're going to see, where this angle here is theta 2. And this also makes sense because if we went the other way on this, if we came in from the right, we'd bend towards the normal for Snell's law. That's what we saw in our last video. We're just going the opposite direction, okay? Well, in theory, what were to happen if you were to bend far, far, far away from the normal line, such that when you came out of the water, you didn't come out of the water? What would happen if this theta 2 was exactly 90 degrees? How would that influence Snell's law? Well, let's just write Snell's law, and then we'll kind of see some of the math that's going to go down here. If we write Snell's law and we recall, we're going to have N1 sine of theta 1 equals N2 sine of theta 2. In our case here, we know that theta 2 is 90 degrees, which means the sine of 90 is defined by the unit circle as being 1. So this equation, it kind of just loses this sine component here. It goes away. That makes this right here, our theta 1, this is what we call a critical angle. If you reach this angle, then you are going to perfectly ride the surface of the water, or whatever medium that you're exiting from, and that light will not actually escape. You're going to be stuck in there. If we want to solve for this critical angle, so let's call this angle here theta 1. Let's actually call it the critical angle here. So this is theta c for crit. If we want to solve for this, well, we need to divide each side by n1. Then what we'd have is the sine of the critical angle, theta c, equals n2 over n1. And then, if we want to find the angle itself, we need to take the inverse sine of both sides. Remember, when you take the inverse function of a function, they eliminate each other. So we find that the critical angle is just equal to the inverse sine, or the arc sine, if you like writing that, of n2 over n1. This will give us some value here for an angle, okay? We also know that this will work in this case because n2 for us, the air, has an index value less than that of n1. That makes this fraction right here some number less than 1. And that's very important because if that number was greater than 1, then all of a sudden I've exited the domain of my sine region. I can't have the inverse sine of like 3. Like, go ahead, type in, inverse sine of 3 on your calculator. It says error, domain. It gives you a mess up. So this is the critical angle forcing theta 2 to be 90 degrees. Now, we can also have an interesting effect occur with the following. What were to happen if you go beyond theta 1? What if your ray, as you're sending it out, pushes that angle even further? What if we take a look at it, What if your angle of the ray is even greater from the normal line? Right? Like the critical angle was back here, we're even further than that. What's going to happen? Well, in this case, what's going to happen is when we go beyond the critical angle, this light, it wants to continue moving away from the normal line. And what's actually going to happen is it's going to reflect back inside of our medium. So down here, recall, is the water, and up top is your air. What's actually going to happen here is this light ray is going to strike the surface and it's going to bounce back down. And what we can say about this is that this water-air shift right here, this boundary layer, this is going to act like a mirror. This is going to be our angle of incidence, and on the other side, this will be our angle of reflection, and they will be equal to one another. So if you go past this critical angle, you're going to have total internal reflection, where none of the light is going to escape, and the light's going to stay inside of the original medium. We actually use this in real life for fiber optics. If you've got a fiber line coming to your house for your internet, or if you're sitting at a telescope station and they're using a fiber line to look at stars, all a fiber optic cable is it's light traveling through the cable. The light holds the information because that light has energy to it, and we just make sure that that light is going to strike at such an angle that the light is reflected back into the fiber optic branch, and it will keep bouncing back and forth and never exit. And it reaches your house at light speed because it's light, and we can pack a ton of information in there. When fiber optics were first starting, we were using low energy light, but as we wanted to get faster and faster internet speeds and more data transmitted, we could use higher and higher energy light, or higher and higher photons of information passing through. So you'll have like X-rays and eventually gamma rays passing through your fiber lines at some point in time in the future, so we can pack more and more information, and you can get more and more of those data tracking ads. Boo. But that's what's going on there with Snell's law. So it's still just Snell's law. It's still n1 sine theta 1 equals n2 sine theta 2. But we just have to recognize that we do have a critical angle. If for some reason we do get a domain error, then that does mean that we are facing back into the boundary layer itself. We're staying in the water. We've gone past our crit angle, and we are going to have total internal reflection. But for now, that is finished. Adios, and you take it easy.